Our last video introduced the idea of a generalized extreme value error structure that could be used to allow for more realistic behavioral patterns in a discrete choice model. In this video, we'll derive the nested logit from first principles. The nested logit model is the most common GEV model due to its simplicity yet realism. In short, it gives a very high bang for buck in terms of adding slightly more complexity, but allowing the model to have a lot more traction as a result. I'll load up some slides that introduce these ideas. As we mentioned in the previous video, somehow we want for there to be some substitutability between the red bus and the blue bus, so that if we introduce a new colored bus, it will cannibalize from the other colored buses and not necessarily from the car, or not by very much. The way that we can do this is by taking our utilities and adding some more structure to the unobservable component of utility. What you see here are the three equations for the total utility that person I gets from riding the red bus, blue bus, or car to work. And there's observable utility associated with that, but then there's unobservables as well. So what's new here is there's a parameter new that governs what's happening at the nest level. And then we also have a new parameter lambda that's attached to our standard IID type 1 extreme value error. And what this parameter new is doing is basically infusing some amount of substitutability into the two buses, or however many alternatives are in the bus nest. This will, in essence, allow for cannibalization type of behavior for new alternatives that are heavily similar to existing alternatives. Now, what's going on with these composite errors? So I didn't tell you what the distribution of nu is. I did tell you that epsilon is type 1 extreme value IID. And it turns out that nu plus lambda times epsilon is also distributed type 1 extreme value, but not IID. If it were IID, then we would have the IIA problem all over again. And it turns out there's a paper by Scott Cardell from 1997 that derives what the distribution of nu has to be in order to get these properties that are computationally attractive, but still allow for a little bit of substitution between the alternatives. If you're curious, this is the Cardell paper, and it's got some pretty heavy math. I just kind of wanted to show you a few things to give you an appreciation for what this looks like. Here, equation 1 of the paper has a integral, and inside the integrand is a ratio of sine of pi times lambda over an exponential plus 2 times the cosine of pi times lambda. So some of this stuff looks almost like made-up math, but just a lot of respect for Cardell and the work that he put into deriving these important results. So what we have here is the nus are coming from this Cardell distribution that has a shape parameter lambda. Some other things to keep in mind about this nested logit error structure. Within the bus nest, we have IIA. I had said that in a prior video, but it's worth revisiting. If we added a yellow bus to the bus nest, then each of the buses would be IIA among each other. And we also have within any nest that these nus are going to have correlation. They're going to induce correlation among the alternatives. So this is precisely what allows for the cannibalization of similar products. We also have IIA between nests at the top level. So therefore, when choosing car or any type of bus, we have IIA. But we definitely do not have IIA between cross-nest pairs. So that is car versus red bus, etc. So if we had a scenario like I discussed in a prior video where there's a 50-50 market share between car and blue bus, this nested logit structure would predict that adding a red bus would change the market share to 50, 25, 25, whereas if we just had a standard multinomial logit, that would only give us 1/3, 1/3, 1/3, which is definitely not realistic given that the red bus and the blue bus are so similar. So that's what we mean by introducing correlated errors into these models so that there's some kind of substitutability between the alternatives. So now that we've kind of derived the error structure, from an estimation standpoint, what we care more about is the choice probabilities. And the reason for that is that that's what we're putting into our likelihood. So these choice probabilities are going to be fairly similar. You'll see that they're sort of a generalization of a multinomial logit. What we have is a ratio of an exponential of a utility divided by a sum of exponentials of utilities. The only difference is that we have an exponential, an extra exponent around the utilities that are exponentiated within a nest. And then to get the derivatives to work out and to get the properties that we need such that the probabilities sum to 1, etc., we're dividing the utility by that lambda here. And then in the numerator of the choice probabilities for one of the nested choices, we're going to have the same sort of exponential over the sum of exponentials. The only difference is that, again, to get the math to work out in the way that we need it to, we're also going to multiply by this sum of the exponentials in the nest raised to the lambda minus 1 power. So hopefully you can see there's a little bit of similarity here, but there's also maybe some counterintuitive complexity as well. But what's nice is that we can factor the probability of choosing red bus into intuitive components. So we can factor it into a term that's what's the probability that I take any bus at all times what's the probability that I choose a red bus given that I chose a bus. So right here, you can readily see that this is just a logit error or a logit probability within the nest. And then across the nest, there's something that also looks like a logit probability, except we have these lambda exponents hanging around. So this is where we can kind of say that at each level of the model, we have something that looks like a type 1 extreme value or an IIA form. But then once we get into any specific alternative, it looks like something that's not IIA. We can also look at the top level probabilities. I just kind of showed you this a little bit at the end of the last slide, but if we just want to think about what's the probability of choosing bus or car, they're going to have this symmetric formulation. And then another thing to keep in mind is that this parameter lambda is going to govern the degree of correlation among alternatives in the nest. If lambda is equal to 1, then I just get the multinomial logit model back. You can easily see that right here. If lambda equals 0, or as lambda approaches 0, then I get perfect correlation among the alternatives within the nest. So lambda, the value of lambda can kind of tell me the degree to which the alternatives are not correlated, meaning that a low value of lambda that's closer to 0 means more correlation. A value of lambda equal 1 means less correlation. And another thing to keep in mind is that if I have more nests in my model, then I'm going to have more lambda parameters. So I'm just going to have a lambda associated with each nest. And we'll get into that in a later video when we talk about some of these GEV steps. So that is the error structure and the choice probabilities for the nested logit model in this very simple car, red bus, blue bus framework. One key thing when determining whether to use the nested logit is to keep in mind that we have to specify ahead of time how the choices are nested. Now, in this example with the car and the different colored buses, that was fairly straightforward, but there are other situations out there where maybe the level of nesting or the organizational structure of the nests might be up to subjective evaluation. So that's something to keep in mind. Also keep in mind that now we have an extra parameter to estimate, that lambda. And we also need to make sure that the lambda falls into the 0 to 1 interval. But at the same time, even though we have these extra complexities in the model, it's also buying us a lot of value in terms of making realistic counterfactual choice predictions in a setting that's still fairly tractable because we still see those flavors of the type 1 extreme value at the different levels of the nesting. Up next, we're going to talk about how we can estimate the parameters of the nested logit model. And we'll talk about two different ways